Hey everybody, uglyShader here with another YouTube video tutorial. And as you are hopefully able to discern from the title, today we're going to be building another rectangular to polar conversion node node group, only it's going to be the three-dimensional version instead of the two-dimensional version. Now, there's a couple differences. One being that obviously the three-dimensional version is going to more accurately represent three-dimensional space. So if you're using this for adding patterns or detail to a volumetric space, the three-dimensional version of the node group will be much more effective than the two-dimensional one. However, there are some other characteristics that they carry that could be beneficial or detrimental depending upon what kind of material you're attempting to produce. So I figure we'll go over those differences real quick and then get right into making the node group. Also, we're not going to cover as much of the theory in this one, so I would suggest watching the first rectangular to polar conversion node group, the two-dimensional one, watching that video before watching this one, just so in case I rush through certain parts of this one, you still have a general understanding of what it is we're doing or why we're doing that. Alright, so let's get into it. This is a texture wrapped around the sphere for the two-dimensional rectangular to polar, or Cartesian, something like that. The square measurements to the round measurements, I guess you could say. And basically what it's doing is it's taking what used to be this, which is just a wave texture applied to a sphere. And it's giving the object two poles, a north pole and a south pole, that all of the points for the texture or whatnot are based off of. So as you can see, we have our north pole and our south pole, and the texture is literally stretching between the two poles. Now, something you might notice is for our two-dimensional one, basically we created two variables. Technically, we created rho and phi. And rho would be the distance from center, the distance from the center point out towards the edge of the sphere as far as where our texture should be located. And phi would be the distance, the angle or whatnot, from the North Pole down towards the equator or from the South Pole up towards the equator. Now, this is different than the one we created in our or in the last video in the sense that it does not have the divide node for its magnitude, for its rho. In that other video, we just threw a divide node in here, or on its rho, on its magnitude, and then just divided it by like 4 or something to kind of straighten those lines out. If we divide by, I believe it's 5,000, they get perfectly straight. But for the sake of this one, we just don't have that in there, and technically it's a good thing because it better illustrates the difference between the two node groups. So yeah, something you may notice is that from our north pole, the band comes down towards our equator and has that bend, and then when it meets the equator, it basically reverses the exact same pattern that it had. It's just inverted, it's backwards. So we literally have something that's up here at the top, and it's kind of snaking like that into the middle, and then it snakes back the other direction. So it's literally just a mirrored version of the top half is what's shown on the bottom half. And that's because we have distance from pole to equator and distance from the center of the object out to the surface, but we don't have the angle that represents how far left to right, or I guess you could say around the equator of this sphere. We don't have that angle. So these swirls get to the halfway point and then just reverse back on themselves. And that's one of the primary differences between the 2D node group and the 3D node group. If I switch to the 2D, you can see that they are up here at the top at the pole, and it literally starts its wave, comes all the way down, and then wraps its wave in on the bottom. So instead of bending at the halfway point and reversing along itself, it continues its pattern all the way down. And if we were to just throw a wave texture on a plane, basically we'd get straight lines running across it. So this is a lot more like what we would actually expect that wave texture to look like if it were put on the sphere and wrapped to its north and south pole. So that's one of the biggest differences and honestly benefits behind the three-dimensional node group versus the two-dimensional, is that the pattern is actually uniform all the way down. And where that would really make a difference is if you were using this particular node group to put textures on like cylinders and stuff. This one should continue to swirl most of the way down the cylinder, whereas the other one's going to go back and forth as it goes down. Another thing that's different about them is that they tend to work on different scales. Like if you recall, excuse me, sorry about that. But if you recall, at just the right scale, we had this vertical seam. Now, mind you, it was very, very mild. Like if I go to 2.5, it's a very, very mild vertical seam, but we have this vertical seam, and it runs from the top all the way to the bottom pole, straight, cuts it straight through. At the right scale on our texture, though, we actually don't have that, and that's not quite the right scale. We still have a little bump there and there, so it's probably like 2.5, 1.5, or maybe 2.52 or something. Anyway, so yeah, we have that seam, but it's running from top to bottom. Now, however, in this one, when the seam shows up, because we're not only giving the angle for top to bottom, but we're giving the angle around the equator, when the seam shows up in this one, you actually get a split all the way around in the 4 points. You get a split on that side and a split on this side. It just runs straight through the north and south poles. But yeah, because we have the equator factored in to this three-dimensional node group, not only do we get a split vertically, but we also get a split horizontally. So again, that's kind of one of their drawbacks, or big differences between them. This one only has the one seam, whereas this one has two seams. Another thing you might notice is that they are running off of different different texture coordinates. And that's just the way they're built, the way they understand the angles. For example, this one, if I were to try and run it off of the object-based coordinates, you can see it kind of still works. Like there's our North Pole, and there's our South Pole. But our poles are a bit closer to each other than they should be, and we got this big, weird deformation of our pattern on both sides. I mean, don't get me wrong, it's kind of a cool pattern and all, but it's not exactly accurate or symmetrical by any means. So we just get results that we don't want when using the object-based coordinates off the two-dimensional node. However, using the three-dimensional node, we have to use the object-based coordinates, because if we use the generated coordinates, well, then we get an entirely different wrong result for what it is we're trying to achieve. So that's another difference between them. Sometimes it may be a limitation depending upon how you're setting your materials up. And mind you, I haven't played with unwrapped objects. I'm not even 100% sure how these node groups would treat a UV map as far as applying their appearance to it. Maybe one of y'all can try it out and let me know down in the comments. But yeah, that's something I haven't even played with yet. Oh, and this less than node up here, try not to worry about that too much. I'm actually just using that as an on-off switch. It's kind of my cheat, so that as I switch between the two materials, you guys don't see the bands break apart and stuff like that and get distracted. I'm just using it as an on-off switch. And what's funny is I've been playing around with these greater than and less than math nodes, and I'm pretty sure that if hooked together properly with the right inputs, because they can work like an on-off switch in the textures and the mix factors and everything like that, I'm pretty sure I'll be able to assemble some logic-based gates, like an AND gate, NOR gates, NOT gates, XOR gates, stuff like that. And if that's the case, that might be really entertaining, because then using some driven number values, you could very possibly have logic-based reactions in your materials depending upon what's going on in the scene and stuff like that. But that's totally for a different video setup or series or whatnot. Anyhow, so yeah, for now, the real big difference is that the three-dimensional is more accurately going to represent volumetrics than the two-dimensional version is, and the three-dimensional one or whatnot just gives you a very different effect for its pattern. They both have their uses. In fact, I can think of a few situations in which the 2D one I'd prefer using. I mean, this kind of pattern wrapped down a cylinder looks more like a candy cane, kind of pattern. However, this pattern, if I were to squish this into kind of like a button shape, would look a lot more like what you'd expect from like a peppermint treat that you'd get around Christmas or whatnot. So, yeah, they all have their different uses. It's just when it comes to representing volumetrics, the three-dimensional node group will be more accurate. All right, so let's go ahead and make this node group. And just a quick glance, this is the group we're building, and we can actually make it a little bit simpler by cutting some of these nodes out. So let's open up a new one, a new file. And I'll turn on screencast keys, get rid of that, and we're just going to add an object to put this on. And I've started to build up a habit of using squares that I then subdivide and smooth. Like that was I subdivided and smoothed it 4 times. And I've just been using cubes or whatnot because then all the geometry on the surface is already made of quads. So if I'm going to play with it later, it's just easier to work with. I don't have 5 and 6 vertice faces. I don't have a bunch of triangles unless I want to triangulate the faces. And then I can triangulate all the faces because they're all quads, and I don't end up with any random shaped faces anywhere. See, I've just kind of started getting in the habit of using a cube to create my sphere just so that it's easier to work with if I'm going to manipulate its surface later. And while I'm at it and I got everything selected, I'm going to pull up my menu again and just hit smooth vertices a few times just to make sure it's good and smooth. Get rid of that, back out of edit mode, and let's pull that menu back up one more time to turn on smooth shading. There we go. That'll work. Now we have something to put our material on. Let's drag this over, switch this one to rendered view, and you know what? We need ourselves a light source. Let's make that light source a little bit brighter, say like 3, and I'm going to rotate it on the x-axis, and then, didn't mean to hit T, escape, T, okay. Then I'm going to rotate it on the z-axis, just bring it around like that, and get a bright side, a shadowed side, and it's not just top and bottom. This window that we drug out, we're going to go ahead and turn into our node editor. Oh, I still have that sun selected. Alright, and with our object selected, let's grab a new material and something that we can manipulate. So let's grab our wave texture. I'm lost. There we go. And let's plug our wave texture in. And then, as always, I'm going to grab a color ramp. And I'm going to tighten this texture up so there's not much gray in it. Let's make the black bands a little thicker. There we go. Now it's kind of like half and half. I guess black's a little stronger than white. That's a little better. Now I'm sure I should move those to like 0.5 and 0.501, and that would be like perfect. I'm sure these aren't perfect, just some sort of optical illusion that makes them look even. Actually, from this angle, it looks like the black's a little skinnier than the white, even though I know there's more black in that image than white. Anyways, I'm going off on a tangent. So yeah, we need to take the coordinates and make it so that instead of it jumped on me. Instead of these kind of poles with the rings on it, it's the bands like we want. Well, on the input side, we're going to need a texture coordinate node, and we'll set that over there. And as I said before, we're going to be using the object-based coordinates for this one. And just like the last one we did, we need to separate x, y, and z out so that we can manipulate our x, y, and z values with mathematical formulas in order to be able to produce the changes we want in our vector information. And as we did last time, I'm going to use a combine RGB node. And again, that's just because, like, I'm sure a combine XYZ node takes care of it. One of these days I'll actually test. However, I want to convert the information that we are manipulating math-wise back into color. I'm sure I've said it before, but if you didn't know, vector information in Blender is controlled through color. So yeah, I use the combine RGB node just because I want to make sure I turn this information that we play with back into something that Blender is guaranteed to recognize as color data before I send it on down the line. So yeah, that's just why I use that combine RGB node. Alright, so let's get to doing this math. I guess it would help if we looked at our formulas first. Let's scoot this back and scoot this back. Alright, so this is the math we have to do. We're going to turn our x, y, and z into rho, theta, and phi. And remember, rho is like the magnitude. It's the distance from the center point to the surface. Theta is going to be like our equator, the distance around our equator, the angle around our equator, and phi is going to be the angle from our pole to our equator. And as you can see, for rho, it's going to be the same as the last time. For our magnitude, it's going to be the square root of x squared plus y squared plus z squared. Theta is going to be the square root of x squared plus y squared divided by z, and then we're going to find the arctangent of that, and that'll be our theta. And our phi is very similar to last time. It's just the arctangent of y divided by x. Only this time we're not going to divide it by half of pi afterward. It's like also for this one, we're not going to balance any of them. The way this one's set up, they should all work with just the basic default x, y values. So let's get started with our rho. That's the square root of x squared plus y squared plus z squared. So we need to build our x times x, our y times y, and our z times z, so that we have our x squared, our y squared, and our z squared. So here we have our x, y, and z. We just need to square them. So I will grab a math node. Now technically I could set this to power and set its second value to 2, and then plug that in. And that'll basically x times x to the power of 2, or x times x. So that would give us our x squared, but I always just end up using multiply nodes and just plugging x into both of them. That way I don't have to bust out on my number pad, because x times x is x squared. So there's our x squared. We can do the same thing for our y squared and z squared. So now we have x, y, and z, and they're all squared. Next step in our equation was to add the x squared to the y squared and then to the z squared. So we just need another math node. Let's set this one to add. Now we add the x squared to the y squared. Oop, I didn't mean to grab that. And then we need another one of those, and we need to add the sum of the x squared plus the y squared to the z squared. So there we have it. We have squared our x, our y, and our z, and we have added all three of them together. Now we just need to find the square root of that product, or of that sum, I guess. And as we talked about in the last one, we can easily find the square root with another math node, because a number to the power of 0.5, or to the power of half, I guess, is the same thing as just finding the square root of a number. 9 to the power of 0.5 is 3. 81 to the power of 0.5 is 9, so on and so forth. So yeah, that's the easiest way to find the square root with our math nodes in Blender. And that is our row. We squared x, we squared y, we squared z, we added them all together, and then we found their square root. X squared plus y squared plus z squared, square root of that. So that is our row. And we will just plug that into R for our combined RGB node, or if you were using a combined XYZ, you just plug that into X. And that'll be our row, our magnitude. Next, we need to build the theta. So we're going to want the arctangent of the square root of x squared plus y squared divided by z. And these are just nested parentheses, nested brackets. So let's see, we got 1, 2, 3 brackets going this way, and that's all the rest of the brackets we have facing that way. And we have 3 brackets on this side. So we start with our innermost bracket, this set of brackets, this set here. So we need x squared plus y squared. That's simple enough. We actually already have our x squared right here and our y squared right here. So I'll just grab this math node and bring this one down, and that is x squared, and bring this one down, and that is y squared. So now we have x squared plus y squared, just like we have right here. This is x squared plus y squared. So we just made another portion of that. So there we go. There's our x squared plus y squared. Now we need to go and do the second set of brackets, the second innermost set of brackets, which will be this here. Now, we've already calculated this, the x squared plus y squared, so we just need to find the square root of whatever the x squared plus y squared was. That's simple enough. That's the same thing we did here. Find the square root. So grab our power to the power of 0.5 and done. There's our square root. Next step, the third or outermost brackets. Okay, well, we've already done this much of that equation, so all that's left is to take whatever our answer from this is and divide it by z. Well, that's simple enough. Let's grab us a divide node. I guess I could have just duplicated one of those nodes. Plug that in there and set this to divide, and we needed to divide it by z. Not the square root of z, or not z squared, sorry, but just plain old z. So we just grab our z and plug that in there. And now the very last step of this equation is, once we have the answer from all of this, we just need to find the arctangent of whatever this number is. Well, we have whatever this number is, now we just need to find the arctangent of it. And that's right there. So we just plug this into our arctan node, and that is done. We have now done the entire equation. We have found the arctangent of the square root of x squared plus y squared divided by z. And we can just plug that in there. The g node on this, or it'd be the y node on a combined x, y, z. And I'm going to scoot these up and just kind of get them out of the way. Saving space on our node group here. It's not too bad. All right, last equation, phi, and like I said, we're going to do the same thing we did last time, only we're even going to skip a step where we divided it by half of pi. So all we need is the arctangent of y divided by x. Well, we start with y divided by x and then just feed it into an arctangent node. We already have a divide node sitting right here, so I'll just make a copy of that. And this isn't y squared or x squared or anything like that. It's just y divided by x. So our y, and we will divide y by x. And then we just need to find the arctangent of that. So we'll grab this arctangent node, duplicate it, set it right there, plug that in, and that's done. That's what's going to be in the B slot, or on an XYZ node, it'd be the Z slot. And that is it. That is everything. That is the whole node group. So we zoom in here and bring this down to the one the other was at, 1.4. And there we have it. Now we have our three-dimensional rectangular to polar coordinate node group. So we can back out a little bit hit box select and grab all of these, and I'll just pull you up, come down to groups, and make a group. Now we want a vector input, but we also want a vector output, and since I'm using a combine RGB node, we don't have one, and gave us an image output, so I'm going to delete that, and then I'm just going to zoom out and drag the vector in to the vector out so that there's a vector point there, and then just plug that in. Now we zoom out and we have ourselves a lot of empty space that used to be filled with nodes. Let's scoot that over. Alright, and there we have our 3D rectangular to polar conversion node group. And like I said, it's real area to shine just because of how it's going to decently accurately, oops, wrong node, represent the texture in 3 dimensions. Where am I going? Okay, there. Its place to shine is going to be in volumetrics. Ooh, that's not very dense. Let's throw a math node in here and multiply that by like 500. Make it super dense. Whoa, that was way too dense. That didn't exactly have the effect I wanted. That's funny. This is the sort of thing that's like bad enough I'd start a tutorial over as far as if this is going to do what I think it's going to do. Come on, get down far enough to actually start separating again. Yeah, because, I mean, technically it's got the swirl to it, but it's so thin that from the side you can see straight through it. Why did you not let me increase the density without going solid? Let's bring the, actually no, let's bring the black way up there. Oh, it's because I'm on add. Oops. That was a really dumb mistake. I just forgot to set it to multiply. Alright, so yeah, let's get you out of there, drag you over. So yeah, as you can see, it really shines when it comes to representing volumetric space in 3 dimensions. As far as giving you that polar effect, that having a north pole and south pole on the object you're working with. Take even more of that out. Make them even thinner. How thin can you get? Oop, went too thin. There we go. And let's go to 1,000 on density. 5,000. Oh, that was 50,000. I guess you're just still a little too thin. There. Yeah, so it's definitely more accurate when it comes to representing the 3-dimensional effects of things. But yeah, that is the 3D rectangular to polar coordinate node group. Kind of an interesting little node group, but again, can be very, very handy when it comes to making different things. And yeah, one more time, we just found, ooh, I guess I didn't need to bring that up. We found the square root of x squared plus y squared plus z squared. Then we found the arctangent of the square root of x squared plus y squared divided by z. And then we found the arctangent of y divided by x. That's all it took. Had to separate it into x, y, z, and then combine it back basically into x, y, z. And you know what? While we're right here, it's a perfect time. Let's delete that out. Whew, that's funny looking. Let's grab a converter, combine x, y, z. Plug that in. You go in the top, you go in the middle, and you go in the bottom. And yep, see, so it's still working. So you can use the combine XYZ instead of the combine RGB. There, I tested it finally. Alright, well, with any luck, you guys learned something useful in this video. Again, if you're kind of missing on some of the theory behind what the heck we just did, I'd check the video I did before this for the 2D version of this node, and also maybe a little bit of the advanced mapping node tutorial I did, because it also talks about how vector information is controlled by color and the different ways that we can manipulate that and stuff. So yeah, there you go. That's the node group. Nothing too special, nothing too hard, especially if you've watched some of my other videos and you're starting to get used to math in Blender. Um, Next up, I believe, is a quick video on the less than, greater than, and how those can be used like on/off switches. Then it's going to be lesson 2 of procedural, or not procedural texturing, but using drivers, the introduction of drivers. And then I should be able to get back to the procedural videos. All right. Well, if there's any questions or comments, go ahead and just drop them down in a link below or whatnot. And oh wait, actually, one more thing before the end. Just like in the other one we did, the 2D one, if you want to straighten those lines out, just throw yourself a divide node into the row, the magnitude, and divide it by, well, like 4. Oh wait, no. That's right. This one has to go way more extreme, I believe. So 5,000. Was it row that you divided by? Well, now, I was really sure that you could straighten those out. I'll look into it. Maybe drop it down into the comments. Oh, maybe it's not row that you straighten out. Maybe it is theta that you straighten out. Math, because that's what's running the equator. Yeah, it's theta, so set that to 5,000 and you get your perfect straight line. So yeah, it's not rho, it's not the magnitude, it's the theta that you straighten in this one because it's what's governing how they meet on the horizon on the equator line. All right, so there you go. Just keep in mind that the 3D coordinate node group runs off of object-based coordinates, whereas the 2D coordinate node group runs off of generated coordinates. Yeah, if you have any questions or comments, throw them down into the comments below. And as always, good luck with any projects you happen to be working on. And until next time, enjoy creating things your way.